Hi, I am Jomara Bahante and I will be your instructor in this course. This course is about graph theory. So for today, I'm going to introduce to you graph theory. And during our discussions, you can ask questions, you can raise your hand here in our platform, Zoom, and you can also type your question in our chat box. Okay, so to introduce myself, my work is on applied mathematics in mathematical modeling. And this topic that we're going to have today is very important because in applied mathematics, in mathematical modeling, networks or graphs are usually used to demonstrate the different interactions among different systems, different agents, different actors. Okay, so to start, let me share my screen. Okay, so we are going to talk about introduction to graph theory today. And most of my lectures that I'm going to discuss are based on the book of Albert Lasso Barabasi. And this book can be accessed from the internet, and I have already shared the link in our Google Classroom. So let me start by defining what is a graph. A graph consists of a set of vertices and a set of edges. For example, we have here four vertices, vertex A, B, C, and D, and these vertices are connected by edges. And we can also name the whole graph. For example, here, we name it graph G. Mathematically, we can write this form to name our graph. So we have a graph G with a tuple of there the V for the set of vertices and E for the set of edges. And the V here is the set of the vertices with vertex A, B, C, and D. And the edges here is a set containing the edge AB, edge BD, edge AD, and edge AC. Now, usually we always hear graph as synonymous to network. And actually they are synonymous, okay? And vertices are also synonymous to nodes, and edges are also synonymous to links. However, in our discussion in this course, we can pertain networks to real systems. For example, here we have a system of connected PCs or computers, and a set consisting of interactions of different actors. And the graphs can be pertaining to the mathematical representation of these networks. For example, in this picture, we know that the set of computers and the set of actors, they are totally different systems. But if you look at this, they're almost the same in their structure as a graph. So we can put that one in this abstract form, in this mathematical representation. So for here, we're going to somehow, networks and graphs are synonymous, but we can pertain this to different systems. Networks pertaining to real systems and graph pertaining to the mathematical representation of these real systems. And graph theory, the history of graph theory is very, very long. It stems from ancient times, like in this one, actually not really ancient as the Egyptians, right? But this actually from the time of the 1735, Euler, okay, have a problem. And actually this is the history of the formalization of graph theory. Graph theory traces its roots back in 1735 in Königsberg, now in Russia. And in that place, Königsberg had 7 bridges across the river, okay, in this town. And there was a problem, a puzzle. Can one walk across all 7 bridges and never cross the same one twice? Okay, so for those students here in our Zoom class, what do you think is the answer? Mm-hmm. Yes. Okay. So Euler, a Swiss-born mathematician, offered a rigorous mathematical proof. And to solve this, okay, he used graph theory. And actually, graph theory is not there yet. Okay, he is the one who started this one, but the theorems, the solution, he used mathematics. Okay, and the answer is there is no such path that you can use. So you can cross the 7 bridges without crossing the same bridge twice. Okay, so he used this formality. He transformed the networks, okay, where the nodes are the different islands and the edges are the bridges to this type of graph. Okay, so let us go back to the previous example, the graph G, and we are going to define different terminologies. Let us name the number of vertices as n, and we can also name this n as the size of the graph. Okay, so when we say size, it means the number of vertices, and L will be the number of edges. Okay, so for example, in our graph G, there are 4 vertices. So this means that the size of the graph is 4, and L, the number of edges, is 4. Okay, so previously, I've shown you a network where there is no direction. Okay, the name that we call that graph is purely as a graph, but we can also call this one as the undirected graph. But here, in what I'm showing you now, we can also have a directed graph or simply a digraph. So let us call this one the digraph H. Okay, so usually the difference is in an undirected graph, if you have an edge ij, it's also the same as edge ji. Okay, but in this example, in a directed graph or digraph, edge ij is not the same as edge ji because probably let's say the vertices are 2 cities, and one direction is a one-way street and the other one is going back but another one-way street. So we know that the 2 edges are different. So examples of digraphs: one-way transportation network, email network, because the interaction, the edge can be represented by one person sending an email, and we know that that person might not reply to you. Okay, and assembly line in manufacturing companies, etc. And in digraph, usually we can also name the edges as arcs. Okay. So let me give you some key properties of nodes. So let us define the degree of the ith vertex, okay, which is the number of edges connected to vertex I. So for example, if we have a vertex A, we know that there are 3 edges connected to vertex A. So the degree of vertex A is 3, the degree of vertex B is 2, the degree of vertex C is 1, and the degree of vertex D is 2. Okay, so that's the definition of the degree of the vertex. Okay, now remember, I've told you L is the number of what? What's L? The number of edges in the whole graph. And actually, we can compute that by using the degrees of the different vertices. So the formula is we sum, okay? We sum all the degrees and divide by 2. Okay, so for example, here we have 3 plus 2 plus 1 plus 2, and divide by 2, we have 4. And we know, right? In this example, we have 4 edges. Now, the question is why? Okay, so students, what do you think? Why the formula is like this? Yes. Yes, actually, that's a good answer, right? To eliminate duplication, duplication in counts. Okay, that's good. Okay, so now I'm going to end my lecture here. I hope you were able to understand the basic of graph theory, and definitely there are more that we're going to discuss in the next lectures. So do you have further questions? Yeah. And if you have further questions that you can ask now, you can email me, and I've already included. I have written my email address in our Google Classroom. And you can also have conversations with your classmates in our Google Classrooms. Okay, so that's all for today, and thank you very much for attending this lecture. Bye.